Hey guys, this is JSer. How's everything going? In this video, I'm going to take a look at 863 all nodes distance k in binary tree. We're given a binary tree, a target, and an integer k. Return a list of the values of all the nodes that have a distance k from the target node. The answer could be returning in order. So suppose the tree like this. We get 5 at the target, and then we need to return. Think about this as a graph without direction. So for 5, the distance with 2 will be 7, 4, and 1, right? Of course, if it is a graph, it might be easier to understand. So we could just start from 5 and do with BFS, right? Breadth first search, and return the elements in the specific layer, and it's done. But we are in a binary tree. We cannot get the parent node. Well, one solution would be just we just add a parent node to all the parent-child relationship. So for 3 got 5, and then we add an arrow to 5 to 3, so we can do BFS now. Well, it's possible, and yeah, for 5, for the elements under 5, well, it'd be just be DFS, right? It's cool. It could be easily done. And if for parents, actually, if the for the parents, we could just do the BFS process recursively, but with less k, right? So go up for one parent, and we search from the search on the other node with the k equals 1, right? So yeah, so the idea becomes, rather than so this is the solution without setting the parent node. So the idea is BFS on the children, go up to kth parent for each parent with BFS on the other branch, right? So how we get to the kth parent? Well, to get kth parent up to, we could just DFS and keep the global stack. All right, cool. Let's begin. First, we create a function called getPath, which is root and target. And then after we get path, we need to create, say, search children at layer, which is root and layer. Yeah. So finally, the target is the target is node, right? Target node. Return the values. Okay. So let's say the result, and we will result push search children at layer, which is target. Okay, right? And then we get the path, target. The path is array, and we move from search from right to left, right? So this is target. So this is k equals 1. So is this k equals 2? So -1, -2. Okay. So for let I equals 1, I equals 2. Okay, so the target here, not here, layer might be 0, means itself. Cool. we check all the children parent up to kth, k and I plus plus. The parent should be path length plus 1 minus I, right? The first one will be 3, so this is it. And then result push search the parent. We need to remove the duplicate. Yeah, we could just filter it out if it is already in it. Okay, if that's the case, I think we could use a set. Use set. And then we here, yeah, we add them in. No. If 5 is our target. If you need to search on the other one. We need to, yeah, I know what happened. We need to check just to get the branch. Directly get the branch. So we check which branch is on the path. So the first element to the right would be 5, right? And we go to 3. This is the 3. Now we can check the 3's left and right to determine what new branch we need to traverse on. So const pref equals path length minus 1 minus I plus 1. Okay. So if parent left equals pref, then we search on the right, right? We search on the right, and okay. So if that's the case, the last element we don't check. We don't check it. We add the last element, which is path length. Okay, or we just do it here. Okay. If I equals k, then result we push parent and continue. If left is so it's on the left branch, we search on the right branch. So result push search on parent dot right. Oh, but if there might be no right branch, right? If it's null, okay, and it might be null. It might be null. Okay, so search on the right with. We already cost 1, 2, right? So means k, no, I. So k minus I minus k minus 1, right? If we go to the k minus, so suppose we search 2 and 2, k equals 2, we go to 1, then we need to search here with 0. Yeah, that's right. So if it's on the right branch, we need to search on the left branch. So left with the same. This is it. This is the basic structure of this implementation. Let's continue implement the details. So how we can get the path? Well, we can create a stack, and okay, the root might be null, right? We're guaranteed, not empty. The target is a node in a tree, so okay. We push root in, and we're only getting the path. So we could just push 1 in, put 5 in. Let's just do something here. Space 3, and then pop 3 out, and we push 3 in, 1 and 5, and pop 5 out, and 3, 1. See that 6, 2. So we push 5 to 6. No, we need to get to the path, so there's no right node in our stack. Okay, so we got 3, and then so we want to push a node, we need to push directly to the node, the last left node. So we push 3, and then 5, 6. When we process 6, if there is right node, we push the right node in, and again, there's no right node, so we pop it, and then process pop 5. There is right node, so we push 5 in, but this is we will come back 5 again, so we add a null as an identifier, and then we push 2. As we did before, we will push directly 7 in, pop 7, and we'll push null to 4. So we will keep full path directly to the leaf node. Cool. So let's create a function called push stack. Okay, so now while stack length is not 0. We get the top element. It might be null as identifier here, but when we add in a null here, we will pop it first, right? So when we pop it, to check if it is the right child. If okay, no. Before we push the right child, we check if it is their target. If top is our target, we just break, right? Yeah, we now get the path, which is 3, 5 here. And now if it is not our target, and we will continue searching. If there's top right, we will stack, we'll push a null as identifier, and then we push stack. Okay, don't forget to push. If there's top right, don't forget to push self back. Stack push top, and push the means push 5 and push a null and push 2 7 in. So push top right. Well, we do this recursively, and here the top, if we made a null, what we do, if top equals to null, It means we need to pop this null and pop 5 again, right? So we pop, we pop next one, not pop, stack pop. Go back null, then we pop 5, and then we continue, right? Yeah. So this gives us the path, which is in a stack. So finally, we will return stack. There might be, if we say we get 7, there might be null. So we filter item not null. So we not get the path. And again, we implement the search children add layer. Well, this is simple. This is the BFS, so we use a queue. We put root in, like layer. Okay, so while queue is not empty, queue is not empty, yeah, if layer is equals to 0, search children, right? We need to return the value. Yeah, if layer is 0, it means this layer is what we want. That's 0, yeah, it's what we want. We return queue map node val. Okay, this is the search children. This is the result. Okay. If not, we will pop them out and layer minus equals to decrement layer and let head add a null as ending identifier while head equals q shift. We shifted it, and if head has left, we push head left. Do the same for right. We will stop when layer is not. When layer is negative, then we stop. Okay. Yeah, we will return layer equals 0. Cool. So this is what if there is no layer? We break. So we at the end we will return empty, right? We should return empty. Cool. So this is it. Let's review our code once more before I try run the code. First, we implement get path. We keep the stack. When push the stack, we push all the way down to the left. And then we process the stack. We get the element out. If it's null, we pop the next one. This is for this is to avoid duplicate push right. Okay, if the element is our target, we break. So the stack will hold the path directly to that node. If there is a right node, like we're going to search 7, we pop 6, and then we go to 5, we pop 5. We found that 5 has right, so we push 5 in, push a null, push 2, push 2, push 7. At 7 we got the target. So and then we filter the item null elements, so we get the path successfully. Now this is to search the specific layer from a root node. We use a queue. We return when layer equals 0. We map the queue to map the nodes to its value. Every time we'll decrement layer and push all the lists out shifted all the nodes and pushed their children in. Okay, so this is okay. And the result, okay. So still we could just use an array here. And the children for target under target node will be easy to handle. So we push search node from target with K. Looks good. If K equals 2, wait a minute. If K equals 2, K equals 2. Okay. And then K is not equals 2. So the next one is 1. So here. And next one is 1. So the next one is here, 0. Okay, this is right. And for path, we get the path. Path is okay, and we loop through the path backward. Gets the parent, and if I equals to k, 1, 2. So 2 pushed in, continue, cool. And we get proof to determine which branch we need to search. If left is our type proof one, then we search on the right. Such the right path, and we need to be the element here should be I, right? This is I, so k minus I, and this one's 1, k minus I minus 1. And finally, return the result. Wow, it's a complicated one. Left undefined parent. So it seems that I have a problem. I didn't make the right path. Night. Empty. This is not good. I am stupid. I shouldn't add the roots as default, but push the root in. We get a 3. Where's 5? I know what happened. I popped. So if it's our the target check, actually, I think should be put before the pop. I'll say stack length minus 1. This is peak, right? If it's target, we break. Sad. Okay. We now have wait a minute. This is hard to see. We now get the path for 3, 5. Cool. And then we get 7, 4, 1 undefined. God. If parent doesn't exist, overflow, right? So the index should be path length minus I minus 1 minus I. It should be bigger than minus 1. There's typo here. Sad. Ooh, nice. Okay, seems working. Let's submit. Shit. Cube map. Node val. The queue is there's null in the queue. Yes, we push null in it, but it will be popped. The input is this. There's null in the queue? Why? Let's log it. Ah, yeah. As I said, the root might be null. Shit. Ugh. Wow, this is actually not that easy. What? Allow me to log the path. Path. Path is 0, 1, 2. The tree. Tree is 0, 1, 2. The target is 2, so the pass should be 0, 1, 2. The pass is okay. To 1. To 1, so the item should be 1. Ah, God. This might be minus. Or layers smaller than 0. The edge case. Still, man. Really? Push parent. Result not parent but parent file. Oh, finally. Come on, yay, finally. There are a lot of mistakes I have made. Anyway, let's try to analyze the time and space. Time, here. We search it, while every node will be traversed for once or twice maximum, so it's linear. We use a stack, so here, time, this is linear. Space, O, stack, so maximum, worst case is linear. And then we will search the children add layer. And again, the worst case is that all the nodes traverse once, right? Even we go to parent, it will be traversed once, and then, yeah, every node will be traversed exactly extra once for the search part. So, and I think it's linear time, space, this use extras. This is stack, and I use another queue. Again, yeah, linear. This is result doesn't count. This is okay. Yeah, so this is it. Hope it helps. See you next time. Bye bye.